Hello, this is the final live stream I'm going to do 2023. It's also the third one in December, so I'm going to do my third advent of code, or attempt at advent of code. They haven't gone very well. I haven't done many advents of code this year, just really the ones I'm live streaming, and a couple at the beginning. So I haven't really got into it, but I'll give tonight's one a go. I'm going to do day 21. And I've had a quick look at it, and I think I'm going to hate it. It looks like one of those problems that's going to become a graph problem, and I'm just a bit shit at those, and it's not really the kind of thing I do a lot of, so I can never remember how to do it. But anyway, we'll give it a go. We'll see how it works out, and I might write some fun Haskell along the way. We'll find out. So this is the challenge. There's some story about a garden and steps, but basically you're given this grid. There's a starting point S where an elf is starting out, and they want to take in the actual puzzle 64 steps, and in the test stuff, the sample stuff, just 16 steps, or 6 steps I think it is. But they start at S and they can take a step in north, south, east or west direction, and they can only step into a cell or position that's got a dot. They can't step into these hashes because they represent rocks. So when they take one step, marked by O's here, these are the two positions they can end up in. They can take one step up and one step left, but they can't go down or right because those are blocked by rocks, or the hashes in this case. And then we take a second step, which is this input. From here, they can step up or down, but not left or right. So they vacated this, but now they're in these positions. And then here, they start here and they can go left or right or down, but not up, because they got the hits, the rock, and so on. They keep repeating it, and then after six steps, these are all the positions they could have ended up in. If you count the number of O's up, or zeros, whatever they are, you get to 16. In 16 places they could have ended up when they started here and took a step. And then the actual input is bigger, it's like this, and they start somewhere in the middle, somewhere here. And they take 64 steps. I mean, to work out how many places they could have reached in those steps. Okay, so that's the challenge. I'm going to try just brute forcing it. It'll probably not work out very well. But I'm going to just start by working out where the S is, and I'll encode all this as a set of rows and maybe the columns as well. And then I'm just going to say, given the starting position, which ones can they step into? And then I'll repeat it where I say, actually I turn this in O to start with, but I'll repeat it and say, given where all the O's are, where can we step into? Something like that. Okay, so day 21. No, not that, sorry. Day 21. Okay, we couldn't do nothing. One thing I was just thinking before I started streaming is the number of steps you take for the test input and the number of steps you take for the actual input is different. So I'm going to change this slightly. I'm going to go from an int to a string to a string. And this is going to be the number of steps, so step count. I might just call it steps, it's a bit shorter. But it's okay, but then in my mains, I need to say day 21, part 1, this is the non-test version, so we take 64 steps. And in the test version, that's the other main, down here, I'm going to take 6 steps, and it's 6 steps. It should lead to the answer of 16 unique places you can end up in. Just quickly make sure I haven't broken anything. I have. It's too many arguments. I didn't save the file. That's why. And now it's got stuck in some weird mode. Second. There we go. So now I've saved the file. Does it run? Yes. Okay, cool. And I'll just check the test still runs, but it should be fine. Yep, failed. Expected 16 steps. Got part 1. Okay. let's start off with breaking up the input. So we want to turn this into a grid, I guess, which is a list of strings, actually, list of characters. Right, let's do delete. So we say something like data grid. In fact, it needs to be data. That we'll find out. But it's basically a list of strings. I'm just going to type a list for now. I'm going to do anything with it. And then what we want to do is we're going to take our input and we're going to call lines on it. And then we want to, sorry, grid is just a list of strings. So we have a list of lines, and that should actually be enough. Actually give us back our grid. And then we'll just show that, but that's not very exciting. So what we're going to do is find the starting point, I guess. So we can say find start, and that's going to go from a grid, and we're going to return a position, and a position is just going to be a pair of ints, an x and a y. So find start. Okay, so find start. If you have nothing left in your grid, we haven't found it. Did not find start. Okay, but if you say find start and you have some row of stuff and then some other stuff, then we're going to say if S is an element of X. Actually, if we use index, then it'll give us the answer back and we have to scan it twice. So we can say something like case L dot index looking for S in X. And if we get nothing back, then we recurse. So we say find start in X's. And if we get just I, we will return I, but then we've forgotten, oh, there's a couple of things wrong. We've forgotten to count the rows as well. What was it? Index of? No. Oh, what is the thing I'm looking for? Google. So we want what are we doing here? We're going from a list of A and some A, and we want to get an int back. No, we're going to get maybe an int. LM index. Okay. We can inline it just to make it look all cool, like LM index of X. It's not in scope, so we'll import it from list. Right. Okay, this gives us half of the things we need. We actually need another position, so it's we're going to say find start is go 0, where go goes from an int, which is our current row, and then a grid, the remaining grid, and it's going to give us back a position. And these will change to be go. So it doesn't matter what the row is in that case, but here we have the row. And whoops, just will give us back a column. And then we return the pair of row and column. Okay, so run this, it should say whatever we start at here. So 1, 2, 3, 4, 5, 6, but 5 really because we start from 0. And 1, 2, 3, 4, 5, 6. So it should give us 5, 5 back because we start from 0 each time. Okay, let's give that a go. Oh, we didn't find a start. So show find start of lines. Try it again. Did not find start. What was I looking for? Lowercase s. Let's try looking for an uppercase s. Got 0, 5. Okay, I keep forgetting. Oops, don't print that. I keep forgetting. Not keep forgetting, but I call find start. We're going to call go of row plus 1 in that. And now you get 5, 5, which is what I was hoping for. Okay, cool. So we found start, but now we need to find the steps we can get to from that position. And I guess we can, from this position, we can look up, down, left and right somehow. And if they are not rocks, then we grab those positions because they're going to form part of our next grid. Or we could just take the grid and set it to we could just update. So for left and right, we can take the current row and we can update it. And then we can also update the row above and the row below. So really, if we go from step, we're going to have some position that we're stepping from. We're going to have the input grid and we will have an output grid. So given some x and y, and some grid, what do we want to do? We want to say we want to adjust the current row. So we can say step row. This is stepping left and right of we're going to take, is it bang or bang bang? I always forget. Something like that. So we'll take the yth row and we will call step row in it. Oh, it'll need the x as well. Where step row is equal to, oh, we've got a column. Right, yeah. X is, here we've got row column, but really it should be column row. Doesn't really matter because it's the same value here, but anyway, X is going to be the column. So X is going to be how far in from here we go. And then we're taking the Y row, so if it's 5, it should in theory get up this row for me. So taking this, we want to say, can we step left and right? So we can call this x's. And what do we want to do here? We know which column we're starting from. So we want to replace a couple of elements here. So we're going to drop stuff until we want to drop stuff before and after, effectively. So we want to say, we know we're at position 5. This is position 4. We want to drop everything before 4. Then look at this. And if it's a rock, it's just a rock. And if it's not a rock, if it's a dot, in fact, if it's not a rock, it doesn't matter if it's a dot or an O, we can still step into it, or even an S. Okay, so if we say break x's at col, that should give us the stuff before. And then we're going to join that onto something like try step, and we are going to go and try and step into x's bang bang col, so the character at that position. And then we're going to take we don't care what happens at the current position. Although we're going to step out of it, but someone else might step into it. We need to be a bit careful with that. Let's just do the first step. Okay, so we don't care if someone steps into it after we step out. So we step out of it. Then we're going to take everything after that point. So we're going to say drop col from x's. Something like that. I'm going to make this go from just a grid to a string. We're just going to look at the row that contains s inside it. So step row is going to go from an int, columns, it's going to go from an int to a string to a string. It's okay, but now we can't break. So break returns, break splits in two, actually. Take is probably what I wanted here. And is it the way around? So take is int list of A to list of A. No. Int, oh, it's wrong around. So int and then list of A. Okay, and then I haven't defined try step. So try step is going to take a character and return int. No, it's going to return a character, sorry. And try step where the character is, oops, a hash, and that's going to be equal to a hash. Try step, anything else is going to be stepping into it. Okay, and yeah, it's going to return a string because that just makes the string concatenation a bit easier. So that's going to be that, and that's going to be that. Okay, a little bit ugly. But anyway, so we find the start. Then we're going to step. If I just, okay, I'm going to need to grab a, I can't do this on one line, I don't think. Okay. Right, so we're going to say let grid equal to lines s. What else we got? Start is equal to find start of grid in show step start grid. Okay, so I'll give that a go, and then we should, in theory, get this row back, but I don't know what's going to happen with S. I think it'll turn it into a dot. And we're out by 1. So dot hash hash dot 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 hash hash dot. Okay, so break seems to be giving back a little bit too much, and drop is not dropping enough. Okay, so take call -1 from that. Kind of let it do this over multiple lines. Okay, so we will do that, and we will drop call +1 from that. Okay, so we've taken one step that way. And now we should also be able to step up and down. So what we can do for that, I think, what I'm thinking actually is I might, instead of just returning the new row, what I might do is collect positions where we can step into. So I'll just build up a list of all those positions, and I'll run through them and generate a new grid. So I'm going to say, so like reached positions. Type of that is going to be a map of position to, oops, let's say 2 like that. It's going to be a map of position to what? To void? Like it, we don't need to store anything, we just want to be able to look it up quickly. So actually, we don't need it to be efficient, right? We can just, we might need to be efficient later, but we could just, oops, have a list of positions. Okay, so step is going to give you back, go from a grid to a list of reach positions. So this is going to go to reached positions. And what positions can we get to from here? Well, it's going to be what I want it to be is maybe a position. So it's going to be try step x is bang bang call. So that should give you maybe a position. And then we say try step x is bang bang. Oops. Actually, it's not call, is it? It's going to be, that was wrong anyway, so it's going to be call -1 and x is bang bang call +1. So we'll look either side and actually gives back a list of maybe positions, and then we can say from maybe, is that right? Cat maybe, maybes. No, what's the function called? So I want to go from a list of maybe A to a list of A cat maybes. I would have got there eventually, but maybe it would have done. cat maybes, and we'll import that. Okay, so if it's a rock, nothing. If it's this, then we need a bit more data, so it's going to be just, and then row, and col. Okay, so I'm going to change my arguments a little bit. Right. So step row is going to take column, so that's our X position, a row, a string. So column, row, and then try step. We're going to say given a row, sorry, column and then a row and some string. Do that. So what we're going to then say is given some column and some row, so an X and a Y, and some S, we're going to say case S bang bang column of, and if it's this, it's going to be nothing. Otherwise, it's going to be just column and row. Get rid of the bracket. Okay, so now with try step, we were going to say col -1, and then the row, and then X's. I just call this S. And then this is going to be try step of col +1, row and S. So now we're going to say step row X, Y, okay, meta position actually, and then that particular row. So now we should get back, when we cut the maybes, we should get back, the only thing we really expect to get to here is 5 and then 4. 4 and then 5 because I'm going X and then Y. Okay, hey Tim, so I didn't notice you joining. Right, so we can step in this. We also want to be able to step in the column as well. So for that, what I might do is transpose it, like the whole thing, swap the X and Y around, and then do exactly the same thing, but in the transposed row. Okay, so so from the starting point, we're going to step row, and then we're going to step col, but we're going to swap these around. We can really just do step row again, and then going to be terribly inefficient here. I'm going to transpose at this point G, then bang bang X this time. So we should be able to step to 4, 5, and also 5, 4. almost. That's going to give us back y and x. So step col is really the same as step row, but we swap the answer around. Is there a way to swap pairs around? So if you've got a pair of x and y, and you want to go to y and x, yeah, it's called swap. Okay. So it's going to be swap of that. No, let's go swap. I thought it was in base. Package base. What's this problem? Data tuple. Can I import it? I can, yeah. And why is that happy? I get rid of some of the warnings. Okay. So swap this, couldn't match type. B0, A0 with pause. But you know, oh, sorry, you need to map this over the result of this. So step column will give you back a list of reach positions, and for each of the things in reach positions, you want to swap the pairs around. So here we need that. Almost. What's this problem here? Oh, this is still step row. Okay, try it again. 4, 5, and 5, 4. Okay, so I can take one step from some starting position. Can I then show it? So we can say something like pp grid, and we're going to go from a grid and some reach positions to a grid. So pp grid, given some G and no more reach positions, we're just going to return that G. Whereas if we have some grid and some position and some remaining positions, what we're going to do is recurse and say pp grid of G prime and the remaining positions, but we need to do something here for this G prime. So what we're going to do, we're going to find that element and replace it. So we're going to find the element at P and replace it with an O. So where replace, and this is going to take some position and a grid and return a new grid. Okay, so replace, we've got an X and a Y, and we've got a grid. And I want to take everything before Y. So we should be able to say take, I think we should be able to say take Y from G. And then we want to add it onto the row. So I'll worry about the row in a second. and then we want to say drop y from G. It's probably y plus 1, to be honest. Y plus 1 from G. Okay, and for the row part, what we want to do, let's say replace row where we pass in the x and we pass in G bang bang y. So replace row given, that's going to go from an int to a string, because that's a component of a grid, to another string. So replace row of x and s is going to be a similar thing, right? So we take x from s and we join it onto an O, stick an O in at that point, and then we drop x plus 1 from G, no, from S, sorry, at that point, K. So this is going to be replace P, G. So we don't actually need to pass the grid in because we have access to it. Oh, no, we don't. Sorry, try again. It's just shadowing. We need to worry about shadowing in a second. It's called G prime or something for now. Okay. So replace row couldn't match character with list of character. G is a grid, so if we take something from a grid, we should be left with a string. So G, the grid bang bang Y, should give me back a string. Character, list of character, expected grid, got a string. First I'm going to do that in replace row. Okay, so grid is list of string. Whoops. So we take y from G prime. That should be a grid. Oh, I see. And that's a grid. Like this has to be a string, not a character. It has to be a list of strings, not a string. Okay. Oh, I'm not pretty printing it. So I wrote all that code and then didn't use it. So we can say show pp grid of step. Oh, sorry, show pp grid of grid and then the step. Okay, so it's hard to read, but you can see we stepped that way. And then the thing above, we stepped in between the two rocks, which matches what we get here. Okay, so now I need to do it again. But this time, we're going to say for every O, we want to take another step. Okay, so for we don't necessarily need to draw this again, right? We just need to say, we know what our positions are. So given those positions, for each of these, we pass them in as being the position and we step from them and we get more reach positions, and we just join it together. So our initial reach positions is just S. And then subsequent reach positions is whatever we got out of the previous step. Well, actually, it's a combination of those. So this is like, this is stepping from a single position, whereas step all is actually going to go from reach positions and some grid to reach positions. So step all, given some positions and some grid, is going to be we can take step position, we can map step over it, and that will give us a list of reach positions. Then we can unique it, or we can flatten it, then unique it, then count how many things are in there. Okay, so we take our list of P's and we map step G over it. So I'm going to swap these arguments around a bit. So the grid is the constant here because we're not modifying that. Okay, should be okay. So step G over our list of positions our list of A is representing a list of positions. Step G should say for everything in our reach positions, apply step G to it. Oh, sorry, that's fine, right? But that gives us back a list of positions. So I need to flatten it. I can't remember the name of this. It's list of A to the list of A, and it's concat. Okay, easy enough. Concat of that. Use concat map. Okay, I think I will. Do a concat map? Yeah, that's fine. And then I think I want to say a nub. Is that the thing? L.nub. I think nub gets rid of duplicates. Removes duplicate elements from a list. Okay. So that really what we can do at this point is replace this original step with step all into the grid, and we're just going to give it a list of start. Apparently not. Oh. It's still around. For some reason, I did grid second here, and then first and the next thing. Anyway, step all, so that we should get the same answer basically. We are this time calling step all rather than step, but with a single position, which is our start position, and then we should find a list of positions we can get to from there. And it looks the same, which is cool. So now what we can do is we can take those positions and we can step all again, so we can get to position 2. So step all gives us back a list of positions. So we can then call step all again. I'm going to sort these arguments around to make this work. Step all, we're just going to put the grid first. And here I'll just swap the arguments around and then add to reduce it. Oh no, it didn't ask me to, so good. Okay. So this is 2 steps. And that's a bit hard to read. So just let me go. What can we do? Go back to test for a second. We're under IO. So failure. Where's failure? Expecting about that. And instead of just doing that, we can say but got. Take a new line there. Oh, we already put strill in. And then I think we can just say print result. Yeah, that's not great. Where are we here? No, we want to go back to main, sorry. Not print result, but print the unlines of result. What's result? Confused now. So what did we get as a result of the, oh, hang on. Here, we don't want to call show, we just want to call onlines. And then back in main, we're just going to print the result. That work any better? Close. Puts that. Put stra. Print will call show on it. That's not really what I want. There we go. Right, okay. So this is what we get, and this is what we want. And we look kind of right after 2 steps. Okay then. So we can now step a number of times. Just to keep writing this function, this should be put somewhere central, but we can say repeat, given some int, and we'll just count down to 0, I guess. Given some function. What's the function going to be? It's going to be, well, it's specifically repeating the steps, isn't it? So step all, where's step all gone? Step all is here. So we could say repeat steps. The number of times we want to do it, the grid that we're applying it to, so let's make the grid constant. Yeah. The grid, the number of times we want to do things, the initial positions, and the resulting positions. So repeat steps of whatever the, whoops, we don't care what the grid is. If we get to 0 and positions, we just return those. So we're done. And then repeat steps, given some grid, some x, and some positions, then we want to say well, we recurse, don't we? So we're going to say repeat steps of G x minus 1, and then step all G positions. So now we should be able to replace this with repeat step two repeat steps. That was grid first, then 2, and then our starting position. Okay, so we have a look at that. We should get the same answer basically. Shrinkify that. That still looks about right, doesn't it? Try and make them line up. Try and make them line up. Okay, so we've got, that looks about right to me. Okay, that's cool. So we actually want to do it over 6 steps. Okay, so 6 steps is going to be the number of steps passed in. So now we should get the grid as it looks at the end. So it should look like this. That looks about right to me. That's cool. So then we just count the number of things in repeat positions. Missed. So instead of unlining it, what we then want to say is we don't want to print it either. We just want to count. So we just take the length of that and we show it. PP grid is not used, but we don't really care anymore. They should say 16. Oh, it did. Okay, cool. So if we say cabal run, it says the part 1, there are this many steps you can get to. Oops. No, it took a while. Okay, that was a bit slow, but it got there in the end. Is that the correct number? So 3,816 places you can get to? That is the correct answer. Cool. Okay. He's reading from the list. His friend numbers are both, but the actual number of steps he needs to get to is this. Okay, we're not going to be able to count that. And the map repeats infinitely in every direction. Yeah. Okay, I'm not going to solve this in the next 7 minutes. And it would take forever. So I'm not even going to attempt part 2 now, I don't think. But I got part 1 working. It's kind of a start. It was kind of fun to do. It was all right to do. I thought it was going to be terrible, but it wasn't. Solution isn't too bad, I don't think, or at least it wasn't too bad to piece it together. It is a bit inefficient though. This transpose, I don't want to do every time. But other than that, this is like having it as a list and then taking the elements out of it is just hideously inefficient. I should really put it in a vector because it doesn't change. The grid never changes when you load it. We just find out, given some starting position, where do we get to, and that would make it a lot quicker. But I'm not going to do that either because part 2 is just too hard. So yeah, thanks for watching along today and throughout the year. I'm going to be away for a bit. I think I'm probably not back until 2nd week in January. So probably about the 11th, I think it's going to be. Yeah, hopefully you can join me then, but I'll put something in Mastodon beforehand, and I'll try and set up a little bit in advance so you know when it's coming. But yeah, thanks for watching and hopefully see you next year. Goodbye.